Hello and welcome, everyone. Today we're going to talk about running tests and simulation with AWS RoboMaker. My name is P.D. Datta. I'm a senior product manager in the RoboMaker team. Later, I'll be joined by Andrew LaFranchise, senior software engineer in the RoboMaker team, and Chris Kruger, director of software engineering at iRobot. Here's what the next 45 minutes is going to look like. We're going to go through an overview of AWS RoboMaker. We're going to dive deeper into running tests and simulation with RoboMaker. We're going to build an architecture for a particular use case. We're going to test CI/CD pipelines. We're going to do a demo that showcases that particular use case. And then we're going to invite Chris to talk about how iRobot is running simulations for their workloads with RoboMaker. Just a quick housekeeping thing. We are also at the networking lounge at the ARIA if you want to talk one-on-one. We are also at the robotics layer at the quad at the ARIA. There are a bunch of engineers there, some cool demos. So if you would like to see some demos, please hang out there as well. So let's get started. What's a robot? When we say that, some of you might be thinking about a humanoid robot. Some of you might be thinking about a rover. Some of you might be thinking about vacuum cleaners at home. To us, a robot is any autonomous machine that can sense its environment, make decisions, and then act upon those decisions in the real world. There are multiple industries where robots are becoming more and more prevalent. It spans across logistics, construction, retail, and consumer electronics. These applications require more and more autonomy, more intelligence for the robots that are operating in those environments. For example, if you have a robot at home, you probably expect that robot to be social, something you can interact with. If you have a robot in the warehouse, you expect that robot to detect obstacles, navigate from point A to point B in the most safe and efficient manner. To give you a general idea, robotics follows the general process of a software development lifecycle. You select a software framework, you develop the application, you test the application, and you deploy that application onto the robot. What's different in robotics is not every developer gets access to that physical robot while testing that application. So you cannot test everything in the real world. And that's where simulation comes in. Simulation enables you to build a virtual environment, a virtual world, which mimics the real world. So you can you can run multiple tests, you can test multiple scenarios, you can fine-tune your application before you actually deploy it onto the robot. The reason why not every developer gets access to the physical robot, there are a couple of reasons, actually. One, it could get very expensive, dedicating hardware to a particular developer. And two, often we've heard from customers that what you do a prototype with is often not what gets developed in production. So let's start with the software framework. Now, selecting the software framework is the first step that you take, and it's probably the most important step as well. ROS, or Robot Operating System, is the most widely used open source software framework in robotics. ROS was founded about a decade ago, and ROS is actually not an operating system. It's a middleware, which is a collection of tools, conventions, and libraries. And then ROS also handles low-level device controls, package management, as well as message passing. The message passing in ROS is a publish and subscribe model. You have nodes, and you have topics. So say, for example, you want to collect CPU utilization and battery percentage from the robot. You create a node that is going to publish those information to a particular topic, say a diagnostics topic. And say you can have a CloudWatch node on the robot that's going to subscribe to that topic, send that data to CloudWatch. So you can monitor the robot from the cloud. Gazebo is a physics-based simulator that was built for ROS. And that's what we use in the RoboMaker service. We launched RoboMaker about a year ago. It's a service that makes it easy for developers to build, test, and deploy robotics applications at scale. Think of RoboMaker to have 3 independent yet integrated features. First, the cloud extensions are something that enables you to extend the capabilities of ROS to the cloud. These are open source packages that you can install as a node on the robot, and then it'll send data to the cloud. For example, you can have a CloudWatch node on the robot that's collecting information from the particular robot, and then sending it to Amazon CloudWatch. So you can monitor the robot from Amazon CloudWatch. Or if you have a node that's getting the video streams from the robot as it moves around in a warehouse, for example, and then stream it to Kinesis video streams in the cloud. Second, we also offer a managed simulation service that you can use to run multiple parallel and large-scale simulations, and it will auto-scale as your simulation gets more complex. Third, we also offer a fleet management capability that enables customers to deploy that application once you've built it securely and over the air onto the robot. Under the hood, we are using AWS IoT Greengrass, which enables you to consolidate multiple robots into a fleet. And then once you're done with your application, you can deploy to that entire fleet over the air. When you go to the RoboMaker console and you want to get started, we have a set of one-click sample applications that you can click through, and then it will set up a sample application, and you can actually see that robot in simulation. From the simulation perspective, you can start, restart, or stop a simulation job through managed APIs in the cloud. Once the simulation job is running, you can spin up the gazebo simulator that you can see from a web-based GUI. Or if you want to visualize what the robot is seeing and you want to interact with the robot in simulation, you can spin up the open source tools such as RViz and RQt. We also log what's going on in the simulation in ROS bag format and then upload it to the customer's S3 bucket that you can use for future analytics. And the simulation service follows a pay-as-you-go model, so you pay only for the resources that you're using. Now, before I call upon Andrew, I wanted to talk about a couple more contributions from RoboMaker. When we launched RoboMaker, we launched in partnership with AWS Educate and multiple university an education program. So educators can get started with a certain set of AWS credits. The AWS RoboMaker badge program enables these educators to get familiar with the basics of RoboMaker and ROS. You can also set up virtual classrooms where educators have multiple students collaborating together, learning about robotics. We also partner very closely with the Open Source Robotics Foundation, who manages ROS. We are a part of the ROS2 Technical Steering Committee. The TSC meets every month, talks about roadmap, and collects feedback and prioritizes features. We also have, so if you go to GitHub, you can go to AWS Robotics, and you can actually find our ROS2 contributions and roadmap to be public. If you are into robotics, we would love to have your feedback so that we can prioritize accordingly. So with that, I'm going to hand it over to Andrew to talk about running tests and simulation with RoboMaker.
Thanks, PD. As PD mentioned, my name is Andrew. I'm a software engineer on the AWS RoboMaker team. I'm going to be talking to you today a little bit about why we think simulation is important for robotic development, in particular why we think testing and simulation is super important for robotic development. And then we'll go through a demo of how we can put together an example CI/CD use case using some AWS services as well as simulation in AWS RoboMaker. So how does testing and simulation help out the robotics developer? We think there's a number of reasons that are super important to test and simulation. The first one is safety. So if you imagine for a moment we are an online retailer and we have warehouses spread out across the country, and in those warehouses we have robots moving from point A to point B carrying packages, and they share the floor with humans. Being able to test that robot-human interaction is super important, and simulation allows us to do that in a way that's completely safe. Repeatability is another big one. If we continue with our imaginary warehouse, you could think of a day when the sun shines through one of our skylights on the warehouse in just such a manner that it reflects off the cement floor and causes the perception stack on one of our robots to act in a way that's unexpected. It sounds like a very contrived scenario, but this stuff happens all the time. We can take that exact input and play it back in simulation to reproduce the issue, fix it, and then write a test around it such that we can ensure that it never comes back. So of course, that's regression testing. But a lot of times when we're developing robotic software, we want to not only perform a regression test with a binary pass-fail, But we're interested in looking at performance metrics, a wide variety of performance metrics across the robot that are being produced in simulation. Simulation allows us to do this, and it allows us to do this in waves. We can set up waves of long-running tests to produce these quality metrics for us over time. And once we do that, we can judge our performance over time as we push more and more code to our robotic code base. Testing in simulation allows us to run tests much quicker than we can in the real world. We can run tests in parallel in simulation, but in a lot of cases, we can also run simulations at sim clock speeds that are faster than wall clock speed. Lastly, we can define scenarios, scenarios for our robots to test in. We can imagine defining a warehouse scenario for our fictional online retailer where we can parameterize every warehouse floor plan that we have across the country. We can parameterize the shelving and the amount of area that the humans share with the robots on the floor. And then we can run tests across this entire set of scenarios to ensure that when we drop a new robot onto the floor of one of our warehouses, it's going to behave the way we expected. And we can take that one step further. So we can randomize some of the input to our scenario. So we can test across a random set of floor plans and a random set of shelving configurations to ensure that when we build a new warehouse and drop our robot in, it's going to behave the way that we expected. So we think there's a number of use cases for testing and simulation that are super important for developing robots. Today, we're going to be looking specifically at how we can programmatically run tests and simulation to build out a CI/CD capability. We're not necessarily going to be looking at any particular type of continuous integration or continuous deployment and delivery feature, but rather, how can we programmatically run our tests and simulation in order to support these kind of use cases? And before we go on to plugging some of this stuff together, I want to talk about the personas that we're targeting for these features. When we talk with companies that are developing robots, we frequently hear them say that they're doing some simulation, but they want to be doing a lot more. And we hear them say, in some cases, they're not doing simulation at all, but they'd love to start. The reason for this is inevitably cost. It's costly for their DevOps engineers to build the integrations to their existing build toolchain in order to kick off tests and simulation and to assess the results of those tests. And it's costly for their QA and test engineers to write the actual tests that run in simulation and then assess the output of those tests because of so much data being produced. So the features we're looking at today are going to be targeting just these personas to make their lives as easy as possible, make it as easy as possible for them to author tests and run tests in simulation. So let's take a look at some AWS services that we can put together to programmatically run tests when we ship code. So PD mentioned before that we have a number of sample applications. Today we're going to write a test for our CloudWatch sample application. That simulation features a TurtleBot, which is a reference hardware platform. And it's navigating around inside our bookstore world. Our bookstore world is a simulated retail space. And the robot's being given a random point to navigate to on the floor, and then it's using its navigation stack to plot a course to that point, and then actually execute a navigation. So on the left-hand side here, we can see the robot's view of the world that it's mapped out with its onboard LiDAR. The little square box there is a robot, and the squiggly line is its path that it's plotted. On the right-hand side, you can see the 3D view of that world coming out of the Gazebo simulator. So we're going to do a simple test today. We're going to test that our robot has successfully navigated to the random point we gave it. And then we're going to add a very simple parameterization of that so we can test that it's made one successful navigation or n successful navigations. So the major AWS service we're going to be using today to trigger this process and then orchestrate it is AWS Code Pipeline. So it's going to be kicked off when we push our code back up to GitHub, and then it's going to orchestrate each step of the process. We're going to be using AWS Code Build to take our software once we've pushed it, build it. We're going to bundle it up, upload it to S3, and then trigger tests running in simulation. We're going to be using a Lambda function to trigger our tests running in simulation. This isn't a necessity. You can use the AWS CLI or SDK to kick off simulations in RoboMaker. But this is convenient for us because it allows us an easy way to define our test when we're creating the sim jobs. We'll talk a little bit more about the document that we're going to be sending later during the demo. But this is available for you to grab off of GitHub and use if you're interested. So a quick note about the tests we're going to be creating in simulation. So we're going to create one test per sim job. This isn't a requirement. Some of our customers like to do this. Other customers like to create a single sim job and run many, many tests in it. It's entirely up to you and your use case. The tests we're going to run today are automatically going to cancel the sim job when they reach a terminal state. And they're going to be tagging the simulation job itself with the output and the final result of the test. So a lot of our customers have their own test reporting framework that they'll hook into. Today, to keep it simple, we're just going to use resource tags on the sim job itself. A note about how we're going to be reporting the tags and canceling the job. PD mentioned before that we work with the ROS ecosystem. Our test today is a simple ROS node. It's going to be subscribing to a metrics topic and looking at the distance to goal metric. And then it's going to be publishing a couple messages to ROS service to cancel the job and to tag the job. These two ROS services are provided in any AWS RoboMaker simulation as convenience functions, which you can use directly from ROS. All right, so this is some of the components that we just talked about. This is what it looks like if you were to put them together to support a notional CI use case. So we're developing our code locally, we're running tests locally, we're going to push our code once we think it's good to go. Before we allow that merge into our integration branch to happen, our code pipeline is going to pick up our merge. It's going to dump it in S3, code build's going to build it, bundle it, upload our deployment artifacts back to S3, and then we're going to kick off some tests and simulation. Similarly, this is what the CD portion of that setup would look like. The same functionality, but likely now we're running a broader set of tests in simulation, a release candidate set of tests, before we stage our deployment artifacts or deploy to our robots. And then putting it all together would look something like this. All right, so let's jump into a demo. We'll actually have a live screencast here of how we can wire these services together. And then we'll push some code and make sure that we see our result get picked up before we get started. So I'll mention that today I'm fast forwarding through a couple of the long range steps. So the build process, the time that the simulation is preparing, we're going to jump forward. So this isn't an accurate representation of how long it would take you, but it does show you the different pieces that you'll need to wire together to make this work. So we're going to start in the Cloud9 development environment. I've already checked out our sample application code, and I've made a small change to our README file. We'll use this change to confirm that everything's working once we get to the end. So we have a simple build spec file here, which we're going to use to configure code build. It's going to install some of our dependencies and some of the code that we'll need to use to build. It's going to actually perform the build for us. And then in a post-build step, it's going to bundle up our resources, put them in S3, and then invoke our Lambda function in order to kick off our tests and simulation. So we'll take a closer look at that Lambda function in a minute. Before we start creating AWS resources, let's take a look at the test itself. So I mentioned before, this is a test node that we've added to the CloudWatch sample application. It's going to be monitoring our metrics topic, and it's going to be looking for a number of successful navigations. We're going to configure that by setting an environment variable for it. As it monitors that distance to goal metric off of our metrics topic, it's going to be calling those that onboard set tag service, and then eventually it's going to programmatically cancel the sim job. So a pretty simple test. Let's go ahead and start creating some AWS resources to wire this together. So we'll go to the code pipeline console. We'll create ourselves a new pipeline. We'll give it a name, and I'm selecting an existing service role here. You can create a new one inline. I already have one, so I'm going to avoid creating a new resource. Now, we can select for our source stage from a number of different locations. We're going to be using GitHub today because that's where our sample application code lives. We can connect to it inline, and we should be able to find the forked repo that I created from our sample application. Here it is here. And then we can grab our feature branch that we'll be using to run tests on. We're going to be using GitHub webhooks in order to automatically kick the pipeline off when we push code. So we can move on to our build stage. So the build stage will be the primary stage for this pipeline. It's going to be pretty simple. You can select from Code Build or Jenkins. Today we'll be using AWS Code Build. And we're going to create a project inline. So we can give our project a name and a description. So we're going to be using a custom image, a Linux-based image. We're actually going to use the OSRF Docker image for Kinetic. It has almost everything we need to perform our build. And we're going to be running our build in privilege mode. And again, I'm going to select an existing service role here. You can create one easily inline, but I'm going to save on my AWS resources for this account. And by convention, the build spec file that we looked at before is going to be pulled in for us. Okay, so let's jump back to our pipeline config. So that's great. Looks like our build step has successfully created, and we can move on from the build stage to the next portion of our pipeline setup. So the next step is going to be our deploy step. For the purposes of this demo, we'll skip the deploy step because all the interesting stuff is happening on the build stage. So we can take a review of what we've created. And all right, that's great. So our pipeline's been created. It automatically is going to kick off a build for us in the background. Once we've copied that source over to S3, the build is going to actually start executing in code build. So this is good. Our resources are created. Everything's looking like it's going to work. We can dive into our code build and take a look at what's happening under the covers there before we move on to our Lambda function. So we've got one build underway, which is good. We've got a little bit of information about the build. Probably the most interesting thing that we can do here is pop open and tail the logs. We can see that we're installing some of our dependencies. So everything looks like it's progressing great now. I'm going to let this build continue, and we'll jump on to our Lambda function and take a closer look at the message that we're going to send it. So the last step of that build step is going to be to invoke this Lambda function with a bit of information about the tests that we want to run in simulation. I mentioned before that we have a very simple scenario specification here where we can name a set of tests that we want to run, and then we're configuring those tests by just setting environment variables. So there's a number of environment variables here that the sample application already needs. The most important one is that navigation success count. So we're going to do one simple test to make sure it does one successful navigation, and then we'll do a second longer running test to make sure it can do 3 successful navs. The rest of that request that we're going to send to the Lambda is a basic create sim job request, and it has all the normal information you'd send to create a simulation job, information about the failure behavior, the role, the location of our robot and sim app, as well as some networking that we need. So if I click test here, we can actually take that document and we should see 2 running simulations in RoboMaker, and we do, which is great. So if we jump into one and we take a look at the tags section, we can see that the test is automatically started to tag. I'm going to pop open a couple of the GUI tools that PD mentioned before so we could see what's actually happening while the test is running. So inside the terminal here, we can take a look at the metrics topic, and we can see that distance to goal metric. As the robot gets closer and closer, it's going to count down to 0. And I'm going to pop RViz open here so we can see that view of the robot sees of the world, as well as the path it's plotting. So if I've done my job right here, we can zoom out on this map of the world, and we should see our robot navigating around. So there's our robot. It's pretty close to its goal. In the background there, I've got the tag section of the sim job, so we can see the tags pop in. So as this value drops to 0, there we go. So that's a successful navigation as far as our test is concerned. The robot's plotted a new course and is on its way. In the background, we should see that tag pop in with reporting a successful navigation for our robot. And there it is. So everything looks like it's going well with our test under the covers. I'm going to jump ahead in time here a bit. This test, I believe I configured for 4 successful navigations. So we should see our last nav pop in here, and we should see the overall result of the test. And there it is. So our test is passed. The simulation should begin to shut itself down. Now you can see it's switched to terminating. And if we go back to our list view, we should see 1 canceled and 1 terminated sim job. So everything's looking good there. Our tests are running. Looks like our build's running. I'm going to jump ahead in time here to the end of the build. And our build has succeeded, so this is great. It looks like all of the components that we have wired up are working. If we go back and take a look at the state of our pipeline, we can see that we've got a successful first pass. So this is great. Let's take a look inside. So our source step completed, our build step completed. So let's see if we can programmatically kick this off. We can check on the 2 simulation jobs that were created out of that first run of our pipeline. And it looks like both of those passed. So there's our multi-nav with 2 steps. And if we go back, we should see our second one passed. So great, let's jump back into the IDE. We've got our README change here. I'm going to go ahead and make a commit. Once we push this back in, we should see our pipeline automatically get kicked off. So I'll add a simple commit message here. This is important because once we see our latest change get picked up, we can ensure that everything is going as we planned. So I'll push this back out to GitHub. And it's pushed. So if we go back to our pipeline, we can see that our source step is kicked off. So this is great. Everything's working. Once that's copied over to S3, we should see our build step begin to process the build against our latest commit. And there it is. And we see our commit there down at the bottom. So that's an example of some of the AWS services that we can put together to programmatically run tests in AWS RoboMaker simulation. I'm very excited now to invite Chris Kruger, Director of Software Engineering at iRobot, to the stage to show us how they run tests and simulation on AWS RoboMaker. Thanks, Chris.
Thanks. Thanks, Andrew. Well, for the past 20 years, I've been very fortunate that I've been able to develop a number of iconic consumer products. Today, I lead the floor care software group at iRobot, and I'm going to tell you a little bit about how and why we implemented AWS RoboMaker. But first, let's start with a little bit on iRobot. So iRobot was started in 1990. It's had some of the most innovative robots in the world, and lots of them. Today, our most popular product, the Roomba, includes advanced features like visual mapping and navigation. It allows it to autonomously navigate through people's houses, similar to autonomous cars. So why do we need simulation at scale? Well, because bigger problems require better tools. And, well, over the last few years, as our products are now expected to navigate through people's houses for up to 30 days at a time without any assistance, our code base has grown tremendously. Where we used to have tens of thousands of lines, we now have tens of millions of lines of code, even in our small little robots. And that leads us to reuse code quite a bit across our products. So code that is used in a mopper may also be being leveraged in our new lawnmower. So with this reusable code and lots more of it, it makes it harder for our robot scientists and our software engineers to develop and to test their code and their algorithms. So what do? No, not exactly. We have extensive test facilities at our R&D center in Boston. We even have a home test lab. It's a 4,400 square foot replica of a house inside the building, instrumented with lasers and cameras that track mission performance across our different products. We also, every iRobot employee gets a free Roomba or Bravo when they start. They're encouraged to use them and test with them. So we have them all over the facility. And finally, we've got thousands of beta testers that, well, as the slide should say, love to give us feedback on our products. So it's a great problem to have. But even with all of this, we want more. Because across all these different products, and when you account for different hardware versions, it's a lot of different products to test. And they're all competing for physical test resources. So some of our robot scientists have developed and maintained simulation, and some of our products have it for some features and some use cases, but not for all of them. And, well, with all of that, it still takes about 6 weeks to get software from our release out into production. And this is where simulation at scale can help us. The scale part of it actually helps drive stability and reliability of the simulation environment. And once we've got a stable and reliable environment, then we start to see the benefits of simulation at scale, where we can concurrently run all of our products and get feedback immediately across our product line on code changes. This allows our developers to move much faster, and developers really are the key customer for us, enabling them to have confidence in the changes they make. So iRobot's entire code base is internally developed, and we have internal tools as well. But we have been using ROS and Gazebo for some time. We like the open standards that it's based on, and it helps us with partners and with attracting new talent. So we attach our simulation environment through a series of ROS bridges back to our code base and our tools. And a managed service like RoboMaker now allows us to have more of our DevOps and test people maintaining and managing the system, and allows our software engineers and our roboticists to spend more of their time developing tests and experimenting. So how did we do it? Well, getting from some simulation to simulation at scale did uncover many issues. So we had teams around the world that were working on this across our development, our DevOps, our QA, and the AWS RoboMaker team was instrumental in helping us as well. And it only took us a couple of weeks to get our Roomba code up and running in RoboMaker, along with our internal tools. So let's take a look. Here you can see our i7 Plus running production code in a semi-realistic home environment. Attached on the side are our internal tools that we use for evaluating our visual navigation and mapping technologies. And it's all running at much better than real-time speeds. It's not sped up. So how we did it? We used Jenkins as our build system. And as Jenkins finishes up a robot build, it triggers a lambda, or triggers a step function that has a lambda that reads a config file. The config file is maintained by our test teams, and it has which tests to run across which robots, and can be changed out as is needed or has the best value at the time. This lambda then, or this step, kicks off another step function, which will then start triggering the simulation jobs and tracking the sim IDs and callbacks, putting them into a Dynamo database. Finally, another lambda is used and pulls the results of the sim jobs that are running, and is triggered by a CloudWatch event. As the results start to pour in, another lambda is used to parse those results and store them in an S3 container. As the results are all finished, we then take that and we aggregate it together, publishing it out to our analytics system and our internal website for general consumption. We then grade those results and pass back a signal to the Jenkins system as to whether the results are good enough to move forward with or not. We use a grading system on the results because there's some variability still in the simulation, and grading is a way for us to kind of account for that. So within a few months, we had this attached to our continuous integration system, and we're using it on our main line to gate all of our code submissions. This provides us basically 40 hours worth of testing on every code submission. And it gives us much better timely results. And our baseline is seeing results from that as well. So we also provided back to our developers, though, some of which like to continue to run locally, Docker images of what we're doing in the cloud. But now the good news is that those Docker images are much more robust than they were before because they're having thousands of tests run on them all the time. Now to see what we did. Well, we're seeing a lot of results from this effort, and while simulation doesn't catch everything, it is really good for behaviors, strategies, and basic interactions. The faster feedback and scalability have benefits that can't be ignored. And the managed service like AWS RoboMaker allows us to focus on the demanding jobs of tough robotics challenges that allow our robots to live in the real world and help make people's homes a little cleaner every day. Thank you. Thanks.
Thank you, Chris. This brings us to the end of our presentation. We appreciate your time. We'll be hanging out here if you have any questions, and we'd love to answer them one-on-one. Thank you.